Today we're going to we're going to see we're going to talk about computed tomography. So it's a leading method of medical imaging and in practice, especially in emergency rooms. So we'll see how it works and and all the math behind it, and how Fourier transform is crucial in how it actually enabled computed tomography. And yeah, so we start with so this is the agenda for today. So we start with basically the forward model of forward model of CT, basically where you send the X-rays through your body. You have an emitter which is set on the other side of the body, and you have a receiver on the other side, and it passes through your body, and that it basically due to the attenuation of the tissues, because it passes through because they absorb some radiation. So then when we receive it on the other side, you basically have a projection of the whole line in which the light is traveling in this direction. So I'll just show you. So basically, if you're sending light with intensity I0 from the tissue, from the other side of the transmitter, so the light attenuates according to this Beer-Lambert's law So what this basically says is, if you have an initial intensity of I0, so this the attenuation happens at the exponent. I mean, if you multiply it with the exponential of the line integral along a chosen line, so the attenuation. So basically, that's what you receive at the other side of the body. So this is nothing but the projection of your tissue onto a particular axis onto a chosen axis on the other side. So this is a small video of how this machine actually looks like. So you see, this area is our transmitter, and all these five. This is a particular configuration of the CT machine. These five things are the receivers. So first, it rotates at a very high speed. Otherwise, if you don't correct it at that speed, your organs will basically get radiated. So that's why you rotate it at a very high speed, and then take the scan by transmitting the light through the body. And the patient sits in between in the circle, in the void in between, right? So this is used. This is advantageous because you can take the whole scan in one rotation of this very fastly rotating body. Whereas in MRI in MRI, you need to sit inside this cabin for like 25 minutes. Let's say if a person comes with a stroke, then you can't. Every minute is basically like a certain. He'll be losing certain probability of surviving. So it's really very well used in the emergency rooms, right? So I'll stop it. So this is, if you observe, so you see these five spheres here. They are the receivers, and whereas I'm sorry, what? Yeah. So whereas this one is the transmitter of the X-rays, and so this is a specific configuration which is used these days. But today we're not going to talk about this configuration. We're just considering a case where you have five receivers like this, and you have five transmitters like this. On the other side, it's basically you're sending parallel rays and not shooting the rays as a beam, like as a diverging wave, right? So okay, let's first for now today we're going to talk about just 2D objects. Let's say our object is just an image. So since we want to rotate so we want to rotate around the body, so we choose to parameterize the line in theta and s, and so let's say this is our body. So we basically project the rays like this with varying s at a chosen theta. So for a particular theta, all the lines through the s are sent in, and So and they are received on the other side. So you're sending rays like this, and you're basically getting, since there is no absorption here, you get the same wave here. So you don't see, so the projection of the body you see on the perpendicular axis of your emission is called the absorption profile, as I wrote here. So this is a, so if you think about it, if it's an image, absorption profile is just adding the number of pixels along a chosen line. Let's say if you're in the last line like this, so it's basically summing up all the pixels, I mean, to the power of exponential minus, so that's why it's going to 0. So, and since the ray is attenuated here, you get something like this, right? So this forward model can be formulated like this. So you basically take an integral over x and y of, when you have a line like this, and each projection for a given s and theta can be written as a double integral over I of x y is our body, and delta is the basically the line function. So for what it means is, whenever this delta shoots, that is, I mean, delta is everywhere 0 except when the one inside is 0. So only when the one inside is 0, the delta shoots, and you get a value, you get this value for a particular, I mean, let's say you choose a particular s and theta, you get this, so you get this value for a particular s and theta. Then you take for another s and the same thetas, then you get this, and basically when you scan along all the s, so you get the whole absorption profile. So this we call it as a forward model, because you're basically forming the signal here. So it's commonly called as a forward model, and then reconstructing, when you're given only the measurements from this forward model, reconstructing back the actual image is called the inverse model. We'll talk about both of them. So this is called the Radon transform. Just this I of xy, its projection onto a for a chosen s and theta is called the on the other side is called the Radon transform. So let's now create two sample bodies and see how the Radon transform looks like for these. So for simplicity, I am choosing just a sphere in the first example. So basically, you assume that you're placing the sphere inside the CT machine, and you have a parallel set of transducers, and you're sending rays. All right. So I'm just creating a circle here, and I took the size to be 180 because it will help us when we with the numerics, because we scan 180 degrees, so it's just easier for us as you see when we progress. So here I'm just creating a circle with I chose a center and radius, and I'm just creating a circle, and whatever is outside is whatever is outside is basically zeros, and the ones inside is 1, right? So this is our first this is the object, and then we'll create a somewhat slightly complex phantom which has two circles, one small one and the one big one, and we'll see and basically they are created with two different circle centers and just different radius, and it's pretty straightforward. So our Radon transform is defined like this. So if you when you choose an angle, so let's say you want to take a projection of this circle from a particular angle like this, right? So for every angle I choose, angle is a single case, and for every angle I choose, let's say I want to measure the absorption profile from an angle of 100 degrees. So what I do is basically I just rotate the image, and then I rotate the image by 100, and just take the summation along the chosen axis, right? So if when I have a circle, and if I just take a projection of it from 100 degrees, so it's basically this. If you change the angle, since it's a symmetric object, and also everything inside is symmetric, like everything is either ones or it's not distributed in a different way. So basically any angle you choose, you get the same measurements, right? So any angle you choose, you get the same, and we'll do it for the next one. So let's see what we get when we so when we scan it from the bottom, so basically you just see a huge bump and a small bump. So and as you change the angle and you measure it from 90 degrees, you see this, right? Because one circle is occluding the other, so you see a huge uh, bump like this, and you basically have the rest, and you can see for other angles. So it's, yeah. It's just summing them. It doesn't mean anything. It just means that how many lines is it traveling through at this particular S. Yeah, just number of pixels in this case. But actually, if you think of it physically, it means the how much absorption happen inside while it is passing through the specific S and theta. So it can it depends on, I mean, it depends on the density and other properties of the tissue. So so now let's do it in all the angles. Like let's sweep from 0 to 180. So we get something like this for one circle, because since it's symmetric, and as we saw that all the measurements are the same along all the angles. Basically, it was x-axis is 0 to 180. Sorry, and this each line in this axis is basically this one, this circle, and so we get something like this, and this is called a sinogram. Sinogram is essentially what we get out of a CT machine. We don't really have this is what we're scanning, and what we're actually receiving from the CT machine is this. At every angle, you're getting the projection, the profile, the absorption profile, and for if you consider the two circle case, so it's like this. So this so initially when you measure from the bottom, you see that the red circle, I mean the huge circle is on the other side, and the smaller one is on the other side. And as they come closer, you see one occludes the other, and you see they're crossing each other, right? So yeah, so the above the both diagrams that are shown above are called sinograms, and yeah, just again. Yeah, so they're basically project. So I want to now see what happens. I mean, let's say we have a sinogram like this, which is shown in the figure like this, and I just want to reconstruct an image. If I an estimate of my image, if I have just this angle, okay. So so what I can do very stupidly is I can trace the ray back, and I can just put the same value of the ray at all the points where it came from. So this is called ray tracing. It's a common technique in graphics, computer graphics. But if you think if we just sum them up on the other side, it's so this is called a laminogram. Basically, it means since it has small value here, you see that it's I'll show you what happens. So now I one more thing. I haven't implemented inverse Radon transform myself, because it involves a lot of numerics, and it needs special attention, because you're basically traversing back the ray, and you have a lot of interpolation to do. So it's so I haven't implemented myself. I'm using this package called Sanketh image. I'll add to the dependencies, and there's in it has iRadon and Radon. Radon is what we basically implemented ourselves above, but this iRadon is how we can do this ray tracing back. Okay, so so now I choose all the angles. So from let's assume that I'm collecting data only from the first projection, and I want to estimate my image, how the image would look like only if I took only this scan. Okay, so let's see. Sorry, maybe one. Yeah, so this is the two circles case. So in the first scan, I saw only this bump, right? So since if we trace the ray back and put the same estimate at all the pixels that are coming from it, so you get this estimate of the image. So as you increase, you can see So I mean, this is basically the first one and the last one are the same, so you get the same image. But if you increase more, so here on the top I'm showing at which angles I'm taking the projections. Okay, so here you see that we saw that in 0 degrees we had a straight we had a huge line like this, and the one like this, and but on the horizontal, it's when it's 90 degrees we saw that a huge I'll show you. So this is basically when you ray trace it back along the whole image, you see the horizontal stripe. It's darker, and it's a little brighter in the center, and it's rather dark on the edges, right? So, and if we have only these both angles, then we get such an image. So we will see as we increase angles, we can get a better estimate of the image, right? So if I took 10 angles, so 0, 20, 40, and so on to 180. So you're kind of forming the image already. I mean, you're getting an idea of what the tissue geometry is inside. Okay, but you see a lot of artifacts, right? So let's assume that we collected the whole scan evenly spanning 180 degrees, and see what we get. So so if you observe, this is not exactly our object, because you don't have any intensity outside the tissue. So what you see here is kind of spilled out some intensity inside towards outside. And let's see why this happens. This shouldn't happen. Okay, right now you can see that there are two objects, but what if in the abdominal region you have a lot of organs which are very close to each other. So once if you reconstruct it this way, so once shadow will go on the other one, and it will totally get occluded. So I mean, we are doing something wrong here. So we'll see what it is. So now, okay, let's recall what slice projection theorem is. So let's consider only one projection profile, which is all from we'll choose a single S, and we'll see what the Fourier of it looks like. Okay, so I'm iterating through all the possible S's, which is basically I'm fixing theta, and I'm changing all the S's, so it's one scan. So if you consider the absorption profile at this point, it's we can represent it as P sigma theta, and now we can put back what we have before what we know before about this P theta S, which is basically the absorption profile, which we understood from here at the top. From here, if you recall, our absorption profile is nothing but the actual object multiplied by the delta function of the chosen of the line at which we are scanning. So if we just put that here, so if we just put that here, so we can just shift some integrals here and there, and so if we can basically what this means is this delta function shoots only if this condition inside satisfies. Okay, so which means that you're basically taking the Fourier transform along only this only along this psi and theta. So I mean, what it essentially means is when you have a Fourier transform of a single projection, it's exactly the same as choosing the particular polar coordinate of the total Fourier transform of a 2D image, and if you choose one angle in which the angle in which we're measuring this, they're basically the same. I mean, I'll show it's better in a diagram. So if this is the object we're scanning, and this is the absorption profile, and if this is the Fourier transform of this object, so if you're scanning along this 45 degrees, so that is exactly, I mean, the Fourier transform of this is exactly the same as when you take a Fourier transform of this 2D image and you pick just the 45 degree line. Okay, so this really helps. So you have a 2D image, and if let's say you measure the absorption profile only along a certain angle. Okay, so this is the absorption profile you get, right? So when you take a Fourier transform of this, it's exactly the same as if you take the Fourier transform of the whole image and you pick the certain polar direction in which you choose from. So this is called the slice projection theorem, and let's see what let's see what it means by choosing just the uh, just the diagonal angle. I mean, which is it can be any angle, but yeah. So if you want to reconstruct this, if you're given this Fourier transform, and if you want to reconstruct the original image, the Fourier transform of a 2D signal looks like this. It's in the continuous case. It's if your FUV is your this is your 2D Fourier transform, and and we want to parameterize everything in psi and theta, because we can so that it's easier for us to interpret it in when we're actually scanning. So so if you choose a u and v to be psi cos theta and psi sin theta, then basically when if you want to change this integrals du dv to d theta and d psi, so we get this integration factor, because the area element of dx dy is not exactly the same as d psi d theta. So it's you get an integration factor of mod psi, if you remember this. So basically when we introduce this, we get that when we have to multiply everything by a factor of mod psi. Okay, is it clear, or okay? So basically what it means is if you think about the Fourier transform of this if you visualize this psi, it's basically a mod x function, like and it doesn't have a defined Fourier transform, if you remember from last class, because the function is not absolutely integrable, and it's not even it's not square integrable. So we have to control its it doesn't have a decaying spectrum. So that's why we have to cut it down at a maximum, and we can create different filters like this. So it's to some these two are some prominent ones. So what essentially we need to take away from this is we can't just sum them up along the axis it came from, but we have to multiply with the filter before, and then take them back to and then you have to multiply it with and then you need to do the ray tracing, right? So that's nothing. I mean, it's an important detail, but it's an important detail, and it's just a single argument in this Radon function. It's called you can you can either put it before we put it as none here, which means that we're not applying any filter on the Fourier transform, like and in this case we want to apply this filter in before we are inverting the total Fourier. So so now we'll see with the one angle. So before, if you remember, we'll see only with one angle. Okay, it's not really evident here. Let's see with the 10 angles. Yeah, okay, and here. See here there's it doesn't spill. The edges are more sharp, and the energy is not spilling out towards outside. So, and if we obviously if we make it 180, you can see it more clearly. So you see that this is more, it's better reconstructed than before. So I probably I wasn't clear, but the essential idea of this is whenever you take actually how you implement filter back projection is you take the Fourier transform of each projection and you keep putting them in the Fourier transform of the big image, right? So before what this says is before you put them, just apply a filter to it, which looks something like this, and no, it's an arbitrary choice. Ideally, you have to do it with this mod this function, this mod psi. So instead, since in continuous case, people if let's consider this one, for example. if your frequency doesn't cross this, it's exactly the same as a normal ramp function, like a normal V. But if you it's just in the case of continuous in the continuous case, it's not defined, so they consider they try with different different such filters. So probably you can also try it with a ramp function. So you so it's I mean, it depends on the, it's not a really well defined choice. I mean, it's there are many filters which you can use. That's what it means. I mean, and in real life you don't I mean, this is not how it is implemented in real life. So it's so you don't really so in real life it's solved as a linear equation, a solution of linear equations, which we didn't discuss, and we'll see it in the future when we talk about denoising and all. So but these are some of the fundamental approaches that are invented in 1980s or something. Okay. So yeah, I'll also come to this later. So I'm taking a slightly more complicated phantom. So it's called the Shep-Logan phantom, and I'm just reading it, and I'm doing this projections from all the angles. So this is the run it. Okay, so this is the sinogram of this phantom, and this is the reconstructed one, which looks close, but it's not exactly this, and you see that you have such an error. You from this, what we can observe is it's able to reconstruct the low frequencies really well, but in the high frequencies, such as the edges, it fails to reconstruct it. Okay, so we'll see why it happens, and it's obviously intuitive. So since what are we doing when we're reconstructing this image? Basically, you're taking angles from all the angles in the Fourier transform, and each projection is each angle there, and when you're collecting them from all the, let's say, 180 degrees, so you're missing some information in between. And when you miss some information in between, it's more evident when you're far away from the center, and less evident when you're closer to the center. So that's why it's able to reconstruct the low frequencies really well, but high frequencies which are far away from the center, it's not able to. It doesn't have the enough energy there to reconstruct. Okay, so so and another one is in here we say 180, but what it means is you basically have a slice of 180 and not really a continuous version of 180. That's why you're losing even this one. Okay, when you discretize it, ideally 180 should work, and if it's continuous, otherwise it doesn't. So in real life, this is not really implemented. You don't really collect all the Fourier samples like this. Instead, you define these filters in the continuous domain. In the time domain. Basically, when you have filters like this, your continuous versions look like this, and you try to do because it's acquiring data at a high rate. You don't try to save them, and it takes a lot of memory. So basically, you just have to convolve with these filters instead of multiplying them in the Fourier domain. You can just convolve with them and get the final image fxy, right? So in real life, it's implemented like this. So it's like I showed in the video. There are different acquisition geometries in which you can acquire the CT. So what we discussed till now is just this case where you have an X-ray source and you scan basically the whole thing like this, and then you rotate it, and then you rotate it, and then you scan again in a different angle. So ideally, today's X-ray machines either use this or this, this is called a fan beam CT, and this is called cone beam CT. Which here you project diverging light rays or X-rays in different angles, and you collect from a curved array here, or and there are papers which show that the math is very similar, and you can extrapolate the case that we discussed here to even these geometries, and cone beam CT is like the latest thing, and so you don't just send it to a single linear array of 1D array of receivers anymore. You send it to a 2D one. So this is more used recently. So yeah, so you can what I was telling before. Previously, people didn't used to do this because this inverse problems is more active in the 80s and not from 60s and 70s. People used to do it like this, and people still compare these results with them. But you can also consider this CT as an inverse problem. I'll tell you what it means. So when X is our image, and when you're projecting, and P is our scanning angle, right? So we can each P can be defined as as A times X. What A contains is the information of which pixel contributed to which projection, how much, right? So let's consider P1. For P1, X1, X7 contributed to P1, X4, and X8. So A has a matrix of where it has ones in X4, X7, and X8, and the rest are zeros. And similarly for all the P's. So basically you have a linear system of equations where you have P's because that's your readings, and you have A, which is your measurement matrix. They call it a measurement matrix, and you want to basically recover X because that's what you're imaging. It's not really 0 1, like in a simplified case when you assume that each pixel contributes equally, so then it's 0 1. Otherwise it's not. So here you just have to invert. I mean, it's not just because you can't really invert the A because A is a huge matrix. If you're talking about 512 by 512 images, then A contains like 512 square of 512 square elements which you can't invert. So this is also ill-posed because you can get several solutions of X from this linear system of equations that satisfy what you want. So nowadays people how they do is they just solve this optimization problem, and the solution, I mean, you can just frame this whole thing as an optimization problem, and you basically have to invert the pseudo inverse of A and not really A, and still you don't get to a good solution because because L2 just solving for this is not a good idea. So in the coming classes we'll see that similar problems will arise even when we're talking about image denoising and all the latest image processing problems, right? So so what you rather do is you assume, you kind of induce a prior on X that okay, I'm not my organs are locally smooth, and my organs have I know that there is some for example, when you take a CT scan and take a gradient of it, you see that the edges are sparse, so you can induce sparsity on the edges. We'll discuss all of these in the class. Alex will discuss. So and recently these methods are shown to reconstruct better looking images because they're just looking because you don't know what you have inside. It's just the best estimate you can get. So recently also neural networks, basically you give to the neural network X as P as the input and X as the output, and you don't model you don't know anything about X, you don't know anything about A, so basically you just try to reconstruct X from P, and you give it a lot of data samples, and it will eventually reconstruct the X. Okay, so now we move to a very different, very much different from what we discussed until now, but in the spirit it's similar. So we see what is called as a half transform, which is a very commonly used computer vision tool. So I don't have a cool image to explain it, but so if you think about if you think about a single point which has 1 here, and you want to see, then many lines can be passing through it, right? So you want to see all the possible lines that can pass through this image. Which are and we want to parameterize these lines in rho and theta, and not in y is equal to mx plus c or something like that. So if we consider this image, then for example this if you have a theta of 0, x-axis is theta and y-axis is rho. If you have a theta of okay, I'll probably write the line equation. sorry. So if you have a line like this, so when you have theta equal to 0 and s is equal to whatever, so here so you can get, if you want to have such a line to pass through this point, you have to put certain values of theta and s, and it can, as you vary theta, your s also varies. So that's what we're going to see here, and we'll see how it can be used as a standard common computer vision tool, right? So so I'm just creating an image, and I'm putting 0 in the center, and I'm just trying to see all the lines that can pass through it, which are parameterized in theta and s. Okay, so it basically gives this. So you get for different angles, you have different s's which satisfy this equation. Right, now I take a line. Now I take a line, and now I want to see which lines can so, and I want to see how this and so this looking at this s and theta is called, you are looking at this half space. So so I want to see the half space of this particular line. Okay, so now I visualize this is exactly the same. This half space is exactly similar as the sinogram that we saw, which is also parameterized on x-axis with the theta and y-axis with the absorption profile, right? So so this is our angles, and you see that all of them are kind of intersecting at one point. I mean, you don't really see the small curves, but you can see that all of them are kind of intersecting at one point, which means that at this particular theta and psi, this is our line equation. This is our line equation, which so at this theta and psi, you satisfy this line. All the points in this point, all the points in this line are satisfying this particular theta and psi and s. So this can be a really powerful tool, because if you want to detect, let's say you want to detect straight lines in an image, so you can just take this image, and you can just look at the points of intersection and of all these bright spots in the half space, and that is basically how you can detect. I mean, yeah, I'll show you. So let's say we have 4 such lines in the image. We'll see what happens now. So basically you get 4 spots, which each of this, since these lines are parallel, the same theta, you get the same theta for all these lines, and you have different s, right? So basically you can just find out how many parallel lines are there in an image, how many lines are there in an image, and we can basically do shape detection. So if you have a lot of let's say you take a image of a lane, then you know that there are going to be some straight lines which are parallel to each other. So you can just look at these both lines and basically say that I mean, it doesn't work that well in practice, but yeah, ideally you can say it. Yeah. So the thing is, you can do the same thing with different shapes. Like, let's say you have circles. All you need to find is a space in which you can parameterize both of them like this, and all the points on the circle can be represented as different curves in the space. And when all of them intersect, basically it means that you have this object in your image, right? So I mean, you can do it for circles, ellipses, and whatever you can parameterize, whatever curves you can parameterize, right? So I took a stupid example now. So I take a bus image, and one more thing to remember is when you're applying this when you're applying this half transform on an image. So okay, and I didn't implement this. I used the package called I imported it somewhere up. Yeah, I used also SK image. We also used Radon Transform from SK image. I imported this thing called half line. So this is for the parameterization of lines as theta and s, and you can do the same for there's I think another function called half circle or something, which can do the same thing for your for circles. You can just test it by taking some standard image with which contains some circles and all that. So okay, coming back. So yeah, so I took some image of a bus. And I assume that I first assumed that this has a parallel line, so it should be able to detect them and all. But uh, yeah, so yeah, one thing to remember is before sending it to the half transform, you should send the edges image and not the grayscale image itself. Either you so I use something called as a canny filter, which is basically like something like a Laplacian convolving with the Laplacian filter like that we discussed in the first class. So you can just do something like that, and just so we get such an image which contains just the edges. And now we use this now we use from a different package. So half lines, I don't know why I did this. Yeah, so also wait, why am I doing this? Okay, never mind. Yeah, so you see that it doesn't work so well in practice. You see one line which it basically detected. And so what I meant to say was, okay, you can ideally you can, if you take some image which has a very well lit scenes, which has straight lines or circles or any definite shapes in it, you can just use these functions from the library, and it's a really cool mathematical it has a really cool mathematical interpretation for it. So that's why I wanted to show it, and it's very similar to Radon Transform, which we saw in like a few minutes ago. And we saw that it detected one line, but yeah, so it has a lot of problems. Basically, if you have different lighting conditions in different parts of the scene, it doesn't work, because firstly you can't detect edges. But what it can work with is if you have discontinued lines, straight lines, then it can work with those. But it can't work with either you have occlusions. Occlusions is a worst case, but still, I mean, if you have different lighting conditions, nothing works. So people usually do neural networks there now, uh, and yeah, so they're not actively used in modern day computer vision. So do you have any questions? Anything? The code is already on GitHub, so yeah, maybe with half comments. so so if you have any questions, you can ask. So I find it particularly exciting, this CT, because it's a really cool tool. And now then in the future we'll also see how to solve this with inverse problems, which is almost to the state of the art. Yeah. So if you have any questions, yeah. Okay, that's it.